Right now, 46,000 feet above the noise of everyday life in a stretch of space so far from home that sunlight itself takes over 22 hours to arrive there, a machine that should have died in 1981 is still awake. It is still listening. And 4 minutes ago, it sent back a signal that has left the people who built it staring at their screens in silence. This is not a machine with cameras aimed at some distant planet. It has no fuel left for dramatic maneuvers. It runs on less power than the bulb inside your microwave. And yet, this half-century-old contraption, held together with 1970s wiring and a memory smaller than a single text message, just became the center of a debate that the loudest voices in science are trying very hard not to have in public. Its name is Voyager 1, and what it just turned back toward Earth, both in data and in meaning, is not something anyone expected to still be hearing about in 2026. Here's what almost nobody outside a small circle of mission engineers is willing to say plainly. This spacecraft was supposed to be a footnote, a 5-year errand. Instead, it has spent the last several years sending home information that keeps forcing quiet, uncomfortable revisions to models that physicists have trusted for decades. And the timing of what just happened, the signal, the recovery, the discovery buried inside it, could not have landed at a stranger moment. Stay with this one. By the end, the sky is going to look different to you. I'm the voice behind Dark Proof, and if stories like this are the reason you're here, stick around, because we're about to go somewhere very few channels are willing to take you. And here's the honest reason most people have never heard the full version of this story. It doesn't fit neatly into a headline. There's no single villain, no single press conference, no tidy ending. It's a slow burn mystery spread across 50 years, a handful of research papers most people will never open, and a mission team that tends to talk about world-changing discoveries in the same flat, careful tone you'd use to describe a weather forecast. When the story is this quiet, it's easy for it to slip past almost everyone. That's exactly why it deserves 20 uninterrupted minutes instead of a 30-second clip. Let's rewind to where this really starts. September 5th, 1977, Cape Canaveral, Florida. A Titan Centaur rocket lifts a spacecraft the size of a small hatchback into the sky, and nobody watching that launch expects to still be talking about it half a century later. The assignment on paper was almost boring. Fly by Jupiter, fly by Saturn, snap some photographs, measure some magnetic fields, and then drift quietly into irrelevance. NASA budgeted for a mission of 4 to 5 years. There was no serious plan for what came after Saturn, because nobody thought there needed to be one. Voyager 1 did not cooperate with that plan. It swept past Jupiter in March of 1979, returning images of swirling storms and, almost by accident, catching a volcanic eruption in progress on the moon Io, the first time an active volcano had ever been observed anywhere beyond Earth. Nobody had planned to find that. It was sitting in the background of a routine navigation photo, and it rewrote what scientists thought they knew about how dead moons were supposed to be. It reached Saturn in November of 1980, revealing braided, twisted rings unlike anything the pre-mission models predicted, and a hazy, orange, nitrogen-shrouded moon called Titan that scientists are, to this day, still trying to fully understand. Mission accomplished, by any reasonable definition. NASA had gotten more than it paid for already, twice over. And then it just all kept going. Every planetary flyby had given it a gravitational slingshot, more speed, more distance, more reason to keep transmitting. By the late 1980s, it had already become the most distant human-made object in existence, a record it still holds today. Engineers who had planned for a 5-year mission found themselves, decade after decade, extending a project nobody had budgeted for because the machine simply refused to stop working. The real turning point, the one that changes this from impressive old hardware to instrument rewriting physics, happened in August of 2012. To understand why, you need to picture the sun not just as a source of light and heat, but as something that blows outward in every direction, a constant stream of charged particles called the solar wind. That wind inflates a kind of bubble around our entire solar system, a region called the heliosphere. Every planet, every moon, every spacecraft we've ever launched, all of it sits inside that bubble. The outer edge of that bubble, where the sun's influence finally gives out to the pressure of the galaxy beyond, is called the heliopause. In August 2012, Voyager 1 crossed it. For the first time in human history, an object built by our species physically left the neighborhood of our star and entered true interstellar space, the region between stars, not a photograph of it, not a calculation about it. An actual instrument sitting inside it, sending data home, and what that instrument found did not match the paperwork. For decades, the leading models describing interstellar space predicted something close to a calm, thin, mostly featureless void. Cold? Yes. Empty, mostly. A kind of cosmic hallway between rooms. Starting in 2017, Voyager 1's plasma wave instrument began picking up something those models had no good explanation for. A persistent, structured hum in the plasma around it. Not a one-off spike, but a sustained signal that kept showing up year after year across hundreds of millions of miles of supposedly quiet space. Researchers publishing on the data were blunt about what it meant. Interstellar space isn't the smooth, sleepy environment the models described. It has structure. It has motion. In places, it behaves less like empty space and more like weather. And the only reason we know this is because one aging machine happened to be sitting inside it when the data started coming in. There's a second twist buried in this same boundary crossing, and it might be the strangest one yet. Before Voyager 1 ever reached the heliopause, the instrument on board designed to measure plasma temperature directly had already failed, back in 1980, shortly after the Saturn flyby. So when Voyager 1 crossed into interstellar space in 2012, it could tell us about density and magnetic fields, but not temperature. That gap in the data sat unanswered for 6 more years. Then, in November of 2018, Voyager 1's twin, Voyager 2, reached the same boundary along a different path, and its temperature instrument was still working. What it measured stopped researchers cold. The interstellar medium just beyond the heliopause wasn't cold and inert the way older models suggested. It was sitting somewhere between 30,000 and 50,000 Kelvin, tens of thousands of degrees, in a region scientists had nicknamed, almost jokingly, the edge of nothing. Now, before you picture flames licking at the hull of a spacecraft, here's the catch. That plasma is so thin, so spread out, that despite the staggering temperature, it carries almost no heat energy in the way we experience heat on Earth. It's less a fire and more a whisper of a fire, spread across a distance measured in billions of miles. But the number itself broke the model. Researchers had predicted a boundary in the range of 15 to 30,000 Kelvin. The real reading came in at roughly double that. The leading explanation involves compression, solar winds slamming into interstellar plasma and squeezing it until its particles speed up dramatically. But the leading explanation is scientist speak for our best guess for now. And what makes this stranger still is that when Voyager 1 originally punched through the same boundary back in 2012, without a working thermometer to confirm it, it still recorded something else nobody expected. Threads of interstellar particles bleeding into the heliosphere ahead of the official crossing, like roots pushing through a stone wall, evidence that this boundary isn't a clean line at all. It's porous, it leaks. And nobody built a model that accounted for that either. Here's the part that stops being abstract and starts mattering to you, specifically. That heliosphere, the bubble the sun blows around us, isn't just a scientific curiosity. It's a shield. It blocks a large percentage of the high-energy cosmic radiation that streams in from exploded stars scattered across the galaxy, radiation that would otherwise reach the inner solar system, and Earth at much higher intensity. If the environment pressing against that shield from the outside is more turbulent, more energetic, and less predictable than our models assumed, that's not a footnote for a physics journal. That's a question about the long-term reliability of the thing protecting every living organism on this planet from the harsher parts of the galaxy. Nobody is saying the sky is about to fall, but the fact that serious researchers now have to ask the question at all tells you how much this one data stream has already changed. How stable is that shield over centuries, not just years? Does it flex and weaken during certain periods of the sun's roughly 11-year activity cycle? And if so, by how much? Could a more turbulent, more porous boundary mean slightly more cosmic radiation reaching the inner solar system during specific windows of time than anyone previously calculated? Nobody currently has a complete answer, and the honest reason for that is almost uncomfortable. We've only ever had instruments inside this boundary for a little over a decade. Every model built before that had to guess. Now, for the first time, we have actual measurements, and the measurements don't fully agree with the guesses. Now here's where the story takes a turn that most coverage of Voyager 1 conveniently skips. In November of 2023, communications between Earth and Voyager 1 didn't go dark. Exactly, they went wrong. The spacecraft kept transmitting a signal right on schedule, but the content of that signal had become meaningless, a repeating pattern of corrupted, unreadable data. For a team that had successfully operated this mission since the Ford administration, this was new territory. The cause turned out to be brutally small. A single chip inside the spacecraft's flight data subsystem, responsible for packaging and formatting the science and engineering data before it's transmitted, had degraded after nearly 5 decades of continuous exposure to cosmic radiation. One component, a fraction of an inch across, had quietly broken down. Fixing it should have been simple. Except the broken part was over 15 billion miles away, with no possibility of a repair mission. And every single message sent to the spacecraft took about 22 hours to arrive, with another 22 hours required for any response to come back. A single round of "did that work?" took nearly 2 days to complete. Engineers at the Jet Propulsion Laboratory spent months in that rhythm. Propose a fix. Send it. Wait a day, check the result. Realize it wasn't quite right. Propose an adjustment. Send it. Wait again. Every step carried the quiet knowledge that a single mistake, transmitted across that vast a distance could end the mission permanently with zero chance of a do-over. What they eventually figured out was that the damaged code couldn't be repaired in place, but it could be relocated. The affected portion of the software was split apart and rewritten to live in different, healthy sections of the spacecraft's remaining memory, then carefully stitched back together to function as a whole again, all guided from a control room on Earth, one 44-hour communication cycle at a time. There was no guarantee any of this would work. The chip that failed couldn't simply be swapped out, the way you'd replace a part in a car engine. There is no garage in interstellar space. Every single test had to be designed as if it might be the last command the spacecraft ever understood. Because a poorly worded instruction sent across that distance, misinterpreted by 49-year-old hardware, could have ended the mission with absolutely no way to undo it. Think about what that actually demands of a person. You write a command, you send it, you wait roughly a full day, you get a response back that isn't quite what you hoped for. You don't get to try again immediately, and you don't get to ask a follow-up question in real time. You go back, reconsider everything, write something more precise, and send it into the dark again, knowing that somewhere between your keyboard and a spacecraft older than most of your colleagues, something could quietly go wrong, and you might never find out why. That was the reality at JPL for the better part of 5 months. And by the spring of 2024, Voyager 1 was transmitting clean, readable data again. And almost immediately, it resumed, sending back more of that unexplained plasma signal from interstellar space, more evidence of the very anomaly that had already forced physicists to start rewriting their assumptions. The machine that nearly went silent forever came back, and it came back with more to say. Ask yourself what that actually means. A spacecraft engineered in an era before scientific calculators were common in classrooms just survived a failure that would have ended most modern satellites permanently, using nothing but patience, careful software surgery, and a communication delay measured in days instead of milliseconds. If that doesn't qualify as one of the more remarkable engineering rescues in the history of spaceflight, it's hard to know what would. There's a second discovery buried in Voyager 1's data that deserves just as much attention and gets a fraction of it. For years, the standard prediction was that the Sun's magnetic field and the galaxy's magnetic field would behave like two separate systems, meeting at the heliopause but staying distinct, like oil and water refusing to mix. When Voyager 1 actually measured the boundary, the reality was messier and far more interesting. The two magnetic environments weren't cleanly separated. They were interacting, exchanging energy through a process called magnetic reconnection in ways the pre-2012 models hadn't accounted for. In plain terms, our solar system and the galaxy around it are not as magnetically isolated from each other as we assumed. There's an active, energetic relationship happening at the edge of everything we call home. And we only know about it because of data from a spacecraft that was never designed to study this in the first place. It was built to photograph Jupiter's clouds. Instead, it stumbled into rewriting a chapter of heliophysics. There's an odd wrinkle here too, one that shows just how much we still don't understand about this boundary. When Voyager 1 crossed the heliopause in 2012, its magnetometer recorded dramatic fluctuations in the magnetic field direction right at the crossing. When Voyager 2 crossed a completely different section of that same boundary 6 years later, it recorded no comparable fluctuation at all. Same boundary, same kind of spacecraft, 6 years apart, and two noticeably different stories about what the edge of our solar system actually looks like. Either the heliopause behaves differently depending on exactly where you cross it, or it behaves differently depending on when you cross it. And right now, with a sample size of exactly 2 crossings in all of human history, there's no way to know which explanation is correct. Now to the part that makes 2026 different from every other year in the spacecraft's long life. Voyager 1 runs on power from 3 radioisotope thermoelectric generators, essentially containers of decaying plutonium-238, whose heat gets converted into electricity. At launch, they produced roughly 470 watts combined. Today, that output has dropped to somewhere around 250 watts, losing a few watts every single year. Because of that decline, mission engineers have already had to permanently switch off several of the spacecraft's original scientific instruments, hard, irreversible decisions made years in advance to stretch the remaining power as far as it will go. But here's the date that NASA itself has now locked in, confirmed down to the second. On November 18th, 2026, at 2:16 and 7 seconds in the morning, Pacific time, Voyager 1 will become the first human-made object in history to reach a distance of 1 full light day from Earth. That's roughly 16. 1 billion miles so far that a radio message sent from mission control won't even arrive at the spacecraft for a full 24 hours, and any reply won't reach us for another 24 after that. Say good morning to Voyager 1 on a Monday, and you won't hear back until Wednesday. No object we have ever built has stood at that kind of distance while still somehow talking to us, and it keeps moving. Every single hour adds tens of thousands more miles between us and it. The power keeps dropping. The list of instruments still switched on keeps getting shorter. At some point in the early 2030s, by the mission team's own estimates, the last usable signal will make that long journey home, and after that, nothing. Bolted to the outside of the spacecraft, completely unaffected by any of this, is something that will outlast the mission by longer than we can meaningfully picture. The Voyager Golden Record. A gold-plated copper disc carrying greetings recorded in dozens of human languages. The sound of ocean waves and thunderstorms, 90 minutes of music spanning cultures across the planet, and diagrams meant to explain where, exactly, in the galaxy, this all came from. Carl Sagan, who helped design it, once described it as a message in a bottle cast into the cosmic ocean. Long after Voyager 1 goes silent, long after everyone reading this is gone, long after most of what our civilization has ever built has crumbled back into dust, that record will still be drifting, carrying proof that something curious once looked up, reached out, and tried. Think about the timeline involved. Voyager 1 isn't heading toward any particular star, but current calculations suggest that in roughly 40,000 years, it will drift within a light year or so of a faint red dwarf called Gliese 4145. 40,000 years. Entire civilizations could rise and vanish in that span, and the spacecraft would still be out there, coasting in silence, carrying a sound recording of human laughter toward a star system that has never heard anything like it. What happens if nothing ever finds it? What happens if, in 100,000 years, some form of intelligence we can't currently imagine finally intercepts that gold disk, and the only trace left of the species that made it is a handful of languages, some music, and the recorded sound of waves against a shore that, by then, might not even exist in the same shape? These aren't questions science fiction invented. They're questions this actual physical object has already made unavoidable. Here's where this story refuses to wrap up neatly, because the honest truth is that scientists still don't agree on exactly what's causing that persistent plasma signal Voyager 1 first picked up in 2017. One explanation says it's a known kind of plasma oscillation, unusual, but explainable within existing physics. The other explanation requires something closer to a genuine revision of how we think the interstellar medium behaves. Telling those two possibilities apart needs more data, and the only instrument currently capable of gathering it is losing power every single year. There is no second Voyager. No follow-up mission built specifically to study interstellar space is funded. And even if one were approved today, it would take at least 2.5 decades just to reach the boundary Voyager 1 crossed back in 2012. Which means whatever this signal turns out to be, the window to find out in real time is closing, on a clock that nobody in Washington or Pasadena gets to extend. Somewhere out there right now, 4 minutes in the past, by the time you're hearing about it, a 49-year-old machine with less electrical power than your kitchen stove light is still speaking, still listening, still carrying a golden record and a stubborn signal that our best models can't fully explain. It has already outlived every expectation placed on it. It's about to become the most distant conversation partner our species has ever had, and it's doing all of this on borrowed time. The signal is still coming. Whether we're ready for what it eventually tells us is a different question entirely. If this is the kind of story you want more of, hit subscribe and turn on notifications, because we're going even deeper into the edges of what we actually know next time. Drop a comment telling me which part of this shocked you the most, and if you know someone who needs a reminder of how strange and vast this universe really is, send this their way.